So hello again. So the doctoral, are you, both of you, right? Arturo, you also?
I'm not
You don't need the doctoral. Okay. So it's then means that just you. And there is, so if someone needs the points of this course as doctoral course, send me an email. Okay, so who is looking? Okay, so let's continue. So today I'll try in a single lecture cover a very important topic of trigonometric approximation and its numerical form, it's FFT, it's fast Fourier transform. So this is essentially the numerical form of harmonic analysis, which is related to the Fourier transforms of functions, but made numerically, which means that on a discrete number of points. And it's extremely useful, so it's a big part of the signal analysis, and many other things are based on this, and FFT is one of the central functions, so in methods. So what we do, so what is it is about? It's about functions. So consider a function f of x on a finite interval. So usually we assume that f of x is periodic. In this case, even if it's not periodic, what is done is that we just close the interval. So essentially we consider, instead of interval, we consider the line modulo 2 pi, which is just circle. So it means that you have an interval from 0 to 2 pi, and this point is associated to the first, right? So we consider the functions. So in other words, or the function x is point on the circle. And another thing which I've tell from the very beginning is that for any other interval, you just can always use a linear transformation. We just maps this, just like we did before with 0, 1, so we can map 0 to pi to AB. So if you want to make this analysis on periodic functions of any other interval, okay, just take linear change of variables. You are going to, so this is obvious. So the trigonometric approximation, and in principle, Fourier series for any functions of this kind is given for the basis functions. So we take basis functions. So basis functions are just, we will take a complex version of the Fourier analysis. So basis function are exponents. So Wj of x is exponent ijx, where in that case I is imaginary unit. So it's exponent with ijx as an argument. And we use the inner product as an average of the product. Or, so if you take two functions, the inner product, so both functions for, let's say, it's not specified so far, but anyway, it's just mean, so the integral divided by 2 pi of f of x times j of x complex conjugated dx. So then we can define a Fourier series of a function f of x. Fourier series will be defined as sum from minus infinity to infinity. So for the indices going through all integer numbers of the coefficients times basis functions, where the coefficients. So what we do, we make a formal. No. Let's do. And before doing it, let's write the orthonormality or conditions. So orthonormality properties is just that if you take Wj, scalar product WL, so what you see, and if it's J, so it's Kronecker delta. So it's 1 when J is L and 0 when J is not L. So this is easy to see because if J is L, it's exponent by its conjugations, it's 1, and then integral gives 1. Right? So if it's J is not L, then it gives you exponent with integer number by I integer number by x, integral is 0, of course. So if you have orthonormality condition, what you can do, and you can think that this is a basis. So let's just formally expand a function into the basis, just formally, without, and then we will prove what it means. So what means, and this expansion is what's called exactly the Fourier series. So Fourier series, what we do is, we expand the function f of x in a basis. So these are functions with j is integer. So j is integer and its coefficients by the function. And also on a formal level, we know that coefficient is just a projection, right? So since it's orthonormal set of functions, so we can, the coefficient is just projection on the corresponding direction. Yeah, so what it is, it's 1 over 2 pi integral. So it's called Fourier series. So only, let's so far write like this. So it's not equal in G. And here we can just remember that there is also a real version of Fourier series. So it's so what you can do. You can, so you see that if function f is real, W0 is 1. So alpha 0 is real. So we can just take A0 to be alpha 0. So this is a real number. And then all other alpha are generally complex. So we can split the real and imaginary part, call it a and minus b, divide by 2. So then when you just substitute both to this sum and assume that f is real, then only real terms all complex terms will cancel. So this is what you probably remember from the from functional analysis. So this will be a plus sum, and then the sum will be already over natural numbers, and it will be aj cosine jx plus j sine jx. So this is a real, just an equivalent to real version of the Fourier series, which is just the same thing, right? So if function is real, it's the same thing. Okay, so so now the first question also, what you study in functional analysis or harmonic analysis in different forms always, because essentially a function f can be very different. All we need for defining this sum is that this integral makes sense. So already you can see that it can be continuous function, it can be piecewise continuous function, it can be even integrable function. So integral is defined, coefficients are well defined, so you can define this sum. So the question, if this sum, which is formal expansion in the basis, has a relation to the original function. And one of the ways how to relate is so this definition, which is this a good thing to know. So the function f of x for x on a circle, arbitrary function. So it's called, we say that it has bounded total variation. If what's essentially called total variation is a supremum for all the sums, good to use I, j, 1 over n. So the sums of the differences, now we will write what it means. So its supremum should be smaller than infinity. So it should be finite, taken for all subdivisions of our interval. So our interval is from 0 to 2 pi. So it's first point we call 0, and then there are next point until the last point, which is 2 pi. So what it means is that you have function considered on the integral or on the 2 pi interval, and then what you do, you take last point, and then you take any points, any set of points arbitrary number, arbitrarily spaced, and then compute sum of the differences. So the sum of the differences, if you take supremum, it's kind of the total. It means that for this function, it will be sum up to the maximum, then from maximum to the minimum, from minimum to maximum. So how much function varies in the full interval? So what is the so it takes into account all variations like positive increase, all increases the function and decreases the function, and so it requires that this should be this total variation should be bounded, limited. So for example, so if f is continuously differentiable, it's bounded total variation. Essentially, you just take maximum derivative, and from this you can derive what's bound for the total variation. Okay. So theorem tells that if f of x defined on a circle is piecewise continuous, piecewise continuous, it includes the functions which are continuous on the interval, but the left and right point are different, because you kind of you associate 2 pi with 0. So 2 pi and 0 are the same points. It's piecewise continuous and has bounded total variation. Then we can compute the sum. So then the Fourier series, we know what it is. So Fourier series at each point is so it's piecewise continuous. So it means that there are some points where the value is actually not so well defined. So we have left limit and right limit, so in general. So the sum converges to the mean value between left and right state. So it means that if the function is at the points where it's continuous, it just converges to the function, and at points when it's discontinuous, it converges to the mean value. That's a theorem. The proof, you can say analysis. And in principle, there are plenty theorems of this kind, which are just telling in which case it converges, in which case it does not converge, and how fast. So anyway, if it converges, it means that, and especially for the function, if it converges, it means at all points except at discontinuous. So it means that we can use Fourier expansion for approximating the function f. So this is what is done. So consider a finite set, which is orthonormal set of functions. So we consider the set of functions which is wj, but j now is from minus k to k. So numerically we cannot take all functions, but we can take a finite number of functions from minus k to k, and then you can use approximation just with these functions. So the best approximation, so best, which means the least squares, mean that with respect to L2 norm, approximation of f of x, remember that it's just projection on the basis of the function. So the best approximation will be the sum from minus k to k, alpha j, w j k x. So we just cut the Fourier series starting from k and k minus k. So now we have a approximation. We know it converges. So the next the practical step is how fast. And this is also classical result from analysis. So another theorem is that if the function is n times continuously differentiable on a circle means that it's also continuously differentiable n times at the ends. And you think that endpoint is 2 pi is continued with 0. So then the difference between, so we should call it gk of x. No? So this is an approximation of order k with k function. So the difference between g and f with a supremum norm, so the maximum difference between all the values at each, or maximum difference at all points, as k goes to infinity, it goes as this big O of 1 over k n minus 1. So in other words, if f is twice differentiable, then the difference should decay as 1 over k, right? So also I will not give a proof. Take analysis. So in particular, the observation that if f is smooth, so infinitely differentiable, then jk of x converges to f of x as k goes to infinity faster than any negative power of k. So any negative power take, it converges faster. And from computational analysis, you probably can maybe remember that if j is analytic function, it converges exponentially fast. Because you can even find exponent, because it's convergence of Fourier series to the function for the analytic function of analytic functions is defined by the nearest singularity, which is outside the real line in the complex plane. So, so this is convergence is exponential for analytic functions. Okay, so again, no proof. Actually, this proof you can see in the book. So if you're interested, so that's, the proofs are rather straightforward. Okay, so so this is classical part. So this is classical part that you learn in functional analysis, and it's very nice. So the question now is how to transform everything into the numerical form. So if you want to compute anything, so this gives you the definition of what is discrete Fourier transform. So discrete Fourier transform. So this is what is new will be new compared to this functional analysis courses. So we consider, so what we do, so we take the integer number n and equally spaced points. So equally spaced xj will be, so it's 2 pi j over n, where j goes from 0 to n minus 1. So n points. We start with 0, as people, numerical people like, start with 0. So these points are assumed to be the arguments where our function is known. So we have point 0, point x1, x2, xn. 2 pi, remember, is the same as x0, right? So this is x. So 2 pi we don't call in any way. And then we have a function. And what means that we have this point is that we only know function at this points on this grid. So this is what we know. Oops. These points we don't need to know because this is the same as the left. So the function is, as I said, usually periodic. So for convergence, we need the function to be periodic and nicely behaved, right? Okay, so this is what we have. So usually we're given n points. So xj and f at xj. So the point and the function in the function value. So what we want to do is we take a if we want to approximate this function by this truncated Fourier series, what you do, you just take one of the ways how you may think of it, and which is exactly this discrete Fourier transformation, is that let's find this trigonometric polynomial in a form which will exactly pass through all these points. So the goal is find a trigonometric polynomial exactly the same as we had. So now the only thing that is different is that, so here we go from minus k to k, which gives you 2k plus 1 points. So here we have just n capital points, which is not necessarily odd. So it's more convenient to sum not from minus k to k, but from 0 to n minus 1. So that essentially doesn't make a difference, but it's more convenient numerically. So we sum from 0 to n minus 1, and then our basis will be I, jx. So just the same as double j. Right? So find this trigonometric polynomial, but now we go from 0 to n minus 1. You see, there is no point to continue this sum, because if you take j equal n, so it will be I n x. But since x is 2 pi over n, this will be just 1. So it will be the same function. So the function for j equals 0 is the same as the function for j equal n. So this is essentially, these are all functions. This lists all the different functions that you can get which are different on this point, exactly on these points. So the other function will be just the same at those points. In between they will be different, but we only know the function at these points. Okay, so find trigonometric polynomial that passes through all points all endpoints, j from 0 to n minus 1. Okay, so we're given points, and we want to find trigonometric polynomial which passing through all these points. Automatically, it will be periodic function, of course, right? Because every term is periodic function. So how you do it? Essentially, you do it in the same way. So we need to find the orthonormal basis. But now, it will be orthonormal basis on these discrete points. So the lemma tells that these functions, they form orthonormal basis if you consider something equivalent of the. So if you consider inner product in this form, so it will be 1 over n over sum from 0 to n minus 1. So this is an average, right, through all points. And then you take this function, multiply by its complex conjugate. L. Okay, so compute it at that point xk. So this is what? This is wj xk, and this is wl xk complex conjugated. And just summing up. So this will be Kronecker delta lg. So this is, so in this sense, these functions, these exponents are form orthonormal basis. So how you do it? So let's write a proof. So this is night property. So we started with continuous functions which has orthonormal properties, and then if it turns out that if we take them on the equally spaced points, they still keep this orthonormality, and the fact that you take them on a finite number of points, it just reduces the infinite number of these functions to a finite number of functions. That's quite nice. So the proof is simple. So what you do, you just compute this sum. So you take this sum, just put the exponents together. Remember what is, okay. Remember what is xk? So xk is this, 2 pi over n. Okay, so now we call all this lambda. And this becomes 1 over n, sum k from 0 to n minus 1, lambda k. So where lambda is and this sum can be computed. So if j equal L In this case, lambda is 1. In this case, the sum is given is just n, and then you give what you wanted. So n divided by n gives 1. So this is okay. And if j is not equal to L, in that case, lambda is not equal to 1. And then we can just take this sum, computed explicitly. It will be 1 minus lambda, n divided 1 minus lambda. Usually, no difference, but let's write it. And now remember that lambda power n is what? It's exponent I j minus L to pi, and cancels, so this is 1. So then this is, sum is 0. So this gives you orthogonality. So essentially, this is a very simple property, but very nicely that whenever you will go from continuous Fourier transform for periodic functions to discrete, where you just take n equally spaced point, you just have essentially the same. Everything is just formally the same step, the same functions, and it still works. And the only difference is that you now just sum through all points. And this is because it does matter, because when you add n, it gives you the same functions on this discrete number of points. Okay, so that means that we immediately have a theorem of how you find the polynomial, trigonometric polynomial interpolating functions at n points, at n equally spaced points. So it's important that it's equally spaced. So the exponential polynomial so now we know how to find it. So it's the exponential polynomial x. Okay, x. We just have to project it on these functions using them as a basis. So it will be that sum, which stands now for in the product, and so it's sum of the function times exponent minus I j x k. So this is an interpolation polynomial, and it is interpolates the points. Interpolates these given endpoints. So the proof, I leave it to you as an exercise. Essentially use orthogonality property, orthonormality. So from orthonormality property, you can prove both that it really passes through each point, and also you can prove its uniqueness as well. Okay. So. Coffee. So for many, some simulations, you take n for 1 million or like this, which means that in principle, by making this approximation, you are doing very, very good, because if you see, if in this case k is large, so which is n, so its approximation is very precise. So the Fourier analysis is a way how to make very accurate, precise calculations. So the practical issue, what does it cost? So the computational cost. So the computational cost is that you need to take sum of f of n values plus exponents for each. So each coefficient requires order n of number of operations. So it's the same thing, but repeated n times. So you have to order n operations to do, and there are n coefficients. Which means that the cost is order n squared in total. And this is bad, because if n, for example, is 1 million, that it means that it will be 10 power 12 operations to make this, and it's impossible. I mean, that it's already very hard computations. So that's why there is a method which is used, and essentially because of this method, this Fourier approximation is so practical, which is called fast Fourier transform. And you will always see it under the abbreviation FFT. So fast Fourier transform. So this will give us, this is a method which requires order of n log n operations. So instead of n squared, you have n log n, and log is essentially nothing, right? So essentially, you reduce n square operation to something not far from n operations. So n log n, which is tremendous increase. So if n was like million, then this will be million. A log is just like 10. So it will be 10 million operations. Okay. So how it's done? So usually in FFT, one takes n to be power of 2. So it's most optimal number. Not necessarily, but the algorithm I will explain is for 2 in some power. And so what you do? So so if n is power of 2, you always can divide n by 2. So you can compute. You can consider the first half and the second half of points. So this is what you do. So taking n as twice m. So what we define? So we take the first coefficients is just I'm just writing that formula that at the end, which is n when I just write explicitly that n is to m. So it's to m, and then there is sum. Okay, from 0 to m minus 1. And so this is for the first m points, and then the next points. So what you do, well, the formula is just the same, right? So just the points now is j plus m, so its points is the same k, and then minus I. So now you have to put j plus m here, but we can split into two exponents. One with j, another with m. Because instead of j, we take j plus m. So I have to put here j plus m. That will be j, and another m. Okay, so these are all, let's go to star. So these are exactly the z expression for all points, but now I split it, just wrote it for the first m points and for the other m points, and I split it j plus m in exponent into pieces. Why not? And now remember that, I'll just put it here, so it's equally spaced point on the interval 2 pi. Okay, good. So the trick is to take a sum and difference. So the trick is just taking sum and taking difference of these points. So taking the sum of each point, each coefficient, Fourier coefficient with Fourier coefficient which is half an interval in front. So you see, it's just very similar expression. So only this term is different, right? So this factor is different. And then the first will give 1, and the second will give this extra exponent. And the secret is that this term is very simple. So now remember what is xk, so it will be 1 plus exponent. So m is n over 2. So now remember that this is n divided by 2, and this is 2 pi over n k. So n cancels, and 2 cancels. So it will be minus k. And this is, so when k is even, this is 1 plus 1. And when it's odd, it's 1 minus 1. Good. So now what you can do is use this property. So I will not keep 2 because 2 will cancel with the 2 from here. So 1 over m. The sum from 1 to 1. And then only even k are important, right? Only even k are important. Because odd terms give 0, and then they just what's remaining. And I already compensated the other 2 with this one. So the next step is just write explicitly that k is, instead of k, you write 2k. So just making the sum only over even numbers. And even numbers, and m is also even because n was power of 2. So that will, the last will be m minus 1. So what we do is that now this k indexes integer numbers. And then what this will be exponent minus ij. And you see it will be 2 pi by 2k over to n over n, but canceling 2, it will be m. So it was originally k over n, but when you just took even numbers, you have to divide by 2, it will become m. Take care about this. Okay, so so this is an expression, and then just the same way. Similarly, you take difference. So and it will be just very similar. So when you do this, you take a sum, you kill the odd terms. When you take difference, you will kill even terms. So the only odd terms will remain. And I will write the final expression. So now this k will index, instead of even, it will be odd numbers. So it will be 2k plus 1. And then exponent minus ij. So it will be 2k plus 1 pi over 2. Oh, no. 2. There's no 2. So instead of, there is something missing, right? So 2k, 2 pi k. I forgot k. 2 pi k, and now it will be 2k plus 1 pi. Plus 1. So instead of odd, will be even. Okay. So in both cases, j now just goes from 0 to m minus 1. And we have this, let's write it 2 star. So we have this system, and this is another way how we write the same coefficient. So we first wrote split it into the 2 groups, the Fourier coefficient, and then they wrote them in terms of sums and differences. And what you can see is that, so what happens? So actually if we forget that we want to compute original, when you compute just the sums and the differences, so you see the sum is twice smaller. So we had that sum which had n terms, and now sum is m terms. Right? So the idea, so this 2 star system, it yields coefficients. So this cj plus m and Cj minus Cj plus m with all m square operations. Yeah, because every sum is just m terms. So that if you have all coefficients, so there's 2m coefficients, and each. So essentially, instead of n squared, so that you decreased amount of calculations by 2, which is from point of view of strict definition of big O, it make no difference because it's just difference by 4. But now we will make it into the difference if we will see that actually you can do this iteratively. So you can do the same thing, but now apply to these expressions. So imagine that you did this, and so what you reduced everything to the computation of the sums which are twice shorter. But now let's say that you can do it again. So let us just call this C11, and this we'll call C12. Yes?
Seria ordem de NN?
Hã?
A ordem desse jeito não seria de N vezes M?
Like this, yeah, something like this, yes. So essentially, this is not good way to write, but just actually, yeah, it's actually mathematically a very bad sentence. So coefficient, it yields coefficients with sums over m equal n over 2 terms. Okay, then this is precise, right? So there were two sums two sums over n terms, and now we have two sums each one over m terms, twice smaller. So now let's see that this can be continued. So we take G. So take the first coefficient, and this is a sum, and we just rewrite it in a slightly different way. So it's 1 over m, sum over k equals 0, m minus 1, so so far it's the same. I only will rewrite exponents. Minus ij k pi, and then I put 2 underneath, m over 2. And then the same thing I will do with another. So j is the number of the coefficient. So now it's sum. 1 is means that it's first level, so next level, and 1 or 2 it means that the first group or the second group. So we write that second expression. Okay, and now we split the exponent into 2 pieces because there is 2k plus 1. The first piece will be just as before. So it's the same, and the second piece will be 1 just pi over m minus I. So compare this system with the one we had in the very beginning, this and that. And you will see that it's certainly well, here there is something not well written. So so when we had xk, there is plus m, j plus m, xk. So it's confused. No, it's not with this we have to compare, or not. So that they must be the same. Up to the substitution so between n, instead of n, you take m, which is twice smaller. So you see the first is correct. So instead of m, you take so n, which was 2m. So you see it's m. And here is instead of, which is xk was 2 pi over n, now it's 2 pi over m. It actually was not necessary to put 2 above it. We can keep it here. And the only thing which is strange is this term. And I think but this term it will be just the same because it's you see it should be the same. G. We did something wrong. Please J. No time. Okay. just find what is the problem. So essentially the idea that we should get the same system as before, but with twice shorter sums. So we can apply exactly the same procedure now to this system. And now expressing the differences. So now we can express the differences for the sums which are to the next level. Express the sums and differences for both as positive and negative. You take sums, sums as difference via sums over m over 2 elements, members, or terms. So you can now again take sums and differences. So and then it decreases number of terms by 2 again. But you see that we started with the same structure. Supposedly we go to the same structure. So when you do this, you again get to the same structure. So you can do it again. And you can do it again until the end. So the full table will be like this. So you have level 1. This is the original. Let's take it to level 0. It is where we had the original Cj coefficients. So it means that we had n constants. Yeah. And if you compute it directly, this requires n square terms, or n square operations. So the next level to which we came right here, it gives us 2 groups of coefficients to n by 2 plus n by 2 coefficients. So we split it into two groups, but each of the groups is given by the sums which twice smaller. But we don't compute these sums. We go to the next level. We split each sum again into two sums which are twice smaller again. So it will be n over 4 plus. So we split the first into the 2 parts, and the second also into the 2 parts. No coefficients. So now it's 4 groups of the coefficients, and each group is given by the same structure of the sum. So we can do it again. And you do it until n is divided by 2 power r. Groups of n divided by 2 power r with just 1 coefficient. N groups. So essentially, when you divide every time by 2 each group, you end up just with 1 number. So it means that order 1 operation for each coefficient, which means that at the last level, we just need n operations in total. So at the last level, each group contains just 1 element, so just not at all a sum. It's just one number. So you just need to compute 1 exponent, but for n different groups. So the last group is n operations. And now from last group we have to go, but these are, you see, every time you go from one level to another, you take differences and sums. So these coefficients are not the same. It's just sums differences of these coefficients. These are sums differences of these coefficients and so on. So you have to go back. So every time you go back, you need n operations. order n operations, because you need to reconstruct, having sums and differences, you can reconstruct original coefficients. So if you have sums and differences, you want to reconstruct the original, you just take sums and differences of those, and so essentially each one you have to connect, like from here to here, you should express Cj and Cj plus m in terms of their sums and differences. Yeah, because and this is for each group, but we all together at each level we have n elements, so each of these operations is n operations. So at the end you have n operation n. So the total number of operations is, and there are levels. So total number of operations are n. But remember, n was 2 power r, so this is, let's select nr. N log 2n. So exactly what we want. So we never computed a single sum, actually, in this procedure. We were substituting the summation by splitting the coefficient into groups and then computing sums and differences. And for sums and differences, half of the terms cancel. And we get the same structure of the sums, and now we split them again until we get to them, and then reconstruct it in the backward direction. So this gives you this is a huge gain, because instead of n squared, you get n almost essentially n log n, so close to n operations. So in MATLAB, and also in many other, in Python and so on, though this is, of course, a simple a function. So you have, in MATLAB, this is called FFT. So FFT is, what it does is it receives number of values of the function at endpoints and returns you the coefficients of the discrete Fourier transform. And if you see that if you do a little bit manipulation, so there is actually not a big. If you have Fourier transform, it's not so hard to go back, because it's essentially changing the j to minus j. So there is also IFFT, its function, which is inverse Fourier transform. So inverse Fourier transform is done in a similar manner and with the same number of operations. So IFFT is where you receive Fourier coefficients, and it gives you back values of the function. So that's essentially that's it. So these property make it extremely useful operations, because as I said, that it's fast, and if the function is periodic, it's very precise. It's highly precise. So this is we will see that this is probably the most precise way how you can compute derivatives, for example, and with a number of operations which is close to any other way of the computing derivative, but which way higher accuracy. And then, on the other hand, if the function is not periodic, it may be not so useful, because if the function is not periodic, it's still convergent. But if it's not periodic, that means that you see it's still periodic, because you associate 0 with 2 pi. But now if the values do not match, now the function is discontinuous, or even if the values are the same, its derivative is discontinuous. So the convergence is much slower. Remember, the convergence was dependent on the regularity of the function. So that's why it's very useful for periodic functions and can be still used for non-periodic functions, but the accuracy decreases substantially. So that's it. FFT now we know.